Okay, we're ready to go. Apologize for the delay. Couple of announcements again. So finally, Soham helped me to fix the auto grader, so it's working. It actually gives you a grade. So if you haven't, if you check your grade and if you think that, okay, if it didn't give you 100, I'll open it up until Wednesday. So please resubmit, try to get to 100. So I don't have to grade it manually. If suddenly you cannot get to 100, then I will take a look at your homework and just essentially say, look, sure, guys, you like, I will take a look through your code and say, and give you a grade. But ideally, it would be nice if you can just fix it because it's reasonably easy, right? And this is you will have to use this source to build further homeworks, right? So it makes sense to debug it, right? Make sense?
Which file do you submit? Does it need to be a folder or how?
So go ahead.
You can just make a zip file with an OS directory. So I think the root of the zip file should be as a CD file.
Oh, the root is source. The root.
No, no,
not the root.
The root should have source and content. Oh, source is not that.
I'll just quickly change the deadline to make sure that it's open until Wednesday. What is that, until 9? It's, what is it, 17th? We cannot look at this. But essentially,
you don't want this to just be one. You want it to be like everything in that one folder.
okay, any questions about the submission structure? Maybe we can push a couple of like short instructions today. But I made sure that it's open until Wednesday. So just please submit. There is like no late penalty, nothing, right? You had a question? Okay, good. Okay, this is good. So and then we hopefully will finish today the interrupts because yeah, it took us forever, but we're almost there. So what I wanted to, like, first of all, maybe any questions about the interrupt processing up until now? Today, my plan is to essentially explain how we can enable interrupt controllers to specifically to enable delivery of hardware interrupts like timer, keyboard, stuff like that. And we take a look at a legacy scheme, and we'll take a look at this modern local advanced programmable interrupt controller and IO Epic bundle, which is de facto standard on modern systems. But before we go there, I just wanted to come back to what we were doing last time. Remember, we were talking about this stack alignment, and we said, okay, and I forget if you forgot that. I apologize if you forgot about it. We said, okay, we're not going to use 8x86 interrupt convention, which is offered by Rust, but instead we'll use our own entry handlers, which will be using naked functions in Rust. And those naked functions, they don't generate prolog, don't generate epilogue. So, and the entire body is just naked assembly, right? And this allows us to essentially do whatever we want on entry. Save any registers, normalize the stack, and then pull the handler from here. Right? And then also do the return as well. Do we remember this from last week? Right? So what is this normalizing? So does this make sense? So Philip's blog pushes for this x86 interrupt. I claim that it's not entirely flexible. And instead, let's just do the normal OS way and write our own assembly code. But instead of writing in assembly, we'll just use this naked assembly to write it from within Rust itself. But this is just really assembly. The reason for going this route, there is like, it's equivalent, whether you write your own assembly or you do it from Rust. The advantage is that this gives you a macro, meaning that you can use Rust macro system to essentially write the code once and then wrap any handlers in those in this assembly prologue and epilogue sequences, right? You can do the same with GNU assembly, which has decent support for macros, but in Intel assembly, which is we used in our as convenient. So that's why, right? So this is probably questions about this. And now I wanted to come back. So imagine this is your kernel stack, the one which is pointed from the TSS stack pointer. And I just wanted to discuss what kind of code we're going to write here to make sure that we normalize the prologue and epilogue. And who can tell me what is this problem of normalization I'm talking about one more time? Sorry, apologize for coming back to it one more time. Correct. And specifically, we can have cases. So we can have a transition from ring 3 to 0. In this case, hardware pushes 5 things, and occasionally pushes +1, which is an error code. And there, we might have a transition from ring 0 to ring 0, since we're running in a kernel with interrupts enabled. And again, the kernel which we will build most of the time will run with interrupts enabled. This is how typically we build modern kernels, just to reduce the interrupt latency, like Linux and all this normal kernel built this way. In this case, we have 3 things pushed by the hardware, and then potentially +1 error code for some exceptions, right? So the question is, I mean, your handler itself is probably takes some kind of a well-formed type-safe data structure, right? Which you define. And typically this data structure will have, okay, I'll ask you a question. What is it should have? And if you will pass the pointer to this data structure inside your handler, and then you can access any field in a type-safe way, right? Make sense? So the question is, question number 1, what's inside this data structure? What do you want to have here? Like what fields? It's a simple question, so go ahead. Don't be shy.
Yes.
Again,
EPS.
what is EPS?
Yes, the DSP.
ESP, okay, you say, look, I should have a stack pointer, RSP, which will point to the value of user stack at the moment when interrupt happens. Sure, yeah. What else?
Consider register state.
Oh, like register, like, what do you mean by register state?
All of the like relevant registers that are, I don't know.
Okay, I agree with you. RAX, RBX, and so on. What is it? R15 on Intel hardware, right? Because all these registers were used by user code. If you don't save them and don't restore them in this epilogue, right, then user will crash, most likely, will return some undefined result, right? Makes sense? So we have to save those. We said RSP because, well, maybe user passes something on a stack, right? And we will use this carefully crafted wrapper macro to access something on the user heap. Makes sense? That's why we need RSP, most likely. And plus for debugging purposes, right? Along with RSP, we will push SS, stack segment. Typically not needed, but let's just do it, right? What else? There's a couple of things left, not many. RAP, correct. No, doesn't matter. RAP code segment. Since hardware pushes, we probably will take R flags. And finally, since hardware sometimes pushes the error code, let me just erase it here. Let's ask for the error code as well, right? So R flags and then error code. Then if it's a well-typed data structure, which of course you push all these arguments in assembly, which is unsafe, but if you say, look, I somehow trust myself and I define the data structure which follows the same layout, and you pass it into this handler, then suddenly it becomes safe, right? And you can access those registers and values in the safe manner, right? Make sense? I agree with this. It makes a lot of sense to have this data structure. Agree with this? Now the question, what about this normalization issue? Because like, as we said, those five, and they are not in the correct order, right, are on the board, and they are sometimes pushed by the hardware, all five plus error code, but only sometimes, and sometimes only three are pushed. And sorry, SS and SF and RSP are not pushed, right? So what are we gonna do with this? How do we solve this normalization issue? We want, like, Philip and his convention are science kind of, I mean, he never talks about it explicitly, right? But really, what can go wrong? There might be some weird case where the data structure on a stack, which you pass a pointer, spills past the stack because the hardware didn't push like additional field, and your stack ends here. And like more specifically says, let's fix the order. So the order, I would just to make sure that we're talking the same language. So RSP and ESP are pushed sometimes. R flags, RAP, and code segments. These three are always pushed, right? And on top of it, some exceptions push error code.
Why does it post both the 64 and 32 different than RSP and ESP?
Why?
That should be a stack.
Oh, sorry. Sorry. This was text. And then here it's up to you. You push all this RAX, RBX. So you control these in your assembly. This prologue, you save them, right? And then R15. Make sense? So how do we deal with this? Do you see the problem? So sometimes if you pass the pointer to the very top of this data structure, which like ends, for example, with R15, it's almost safe for as long as you don't access these two fields. But they, technically speaking, may not be present. You can ask a question like, what are you talking about? Because if we're already running inside ring 0, and these three are pushed on a stack, let's imagine the error code is also pushed, and we pushed everything else. This is our type safe data structure. Since we were running in ring 0, you say, look, but these two fields, wow, there was some stack before, so that must be there, right? Already. Is it true or not? Can someone come up with a case when, like, this data structure spills past the kernel stack and the TSS actually was pointing here? And if you try to access those fields, it will really result in a SAC fault. What can it be?
Could it be when it crosses the phase boundary?
When it crosses what?
Well, you're saying.
Yeah, page boundary, right?
Yes.
Right, but under what conditions? Like,
I don't know.
yeah, it's a little hard to come up, but maybe someone knows. It's nice to kind of explore.
Or maybe if the stack is empty before this is pushed. So that seems unlikely.
It seems unlikely, but it seems possible. And it's important to understand that those very weird corner cases are still possible. Normally, you would say, and I assume this is what Philip is saying, that, or I mean, more specifically, what the greatest thing is that, which defines this polling convention, is that these two fields are only valid when you transition from ring 0 and not from ring 3. When you transition from ring 3 and not from ring 0 into ring 0, right? Which is kind of like it's beyond the language. It's like kind of like patching C with all this additional rules, but you know it's underdefined, and then the compiler can result in undefined behavior. So it's very, very awkward to say that these two fields are valid and can be accessed in your code, but only under certain conditions, right? So I would strongly argue, let's avoid it. If we're saying designers, let's just avoid this case, right? So the question, like, when can it happen? As you say, it's past the page. Imagine our stack page is this, and stack was empty, but you were already, how come it can be empty and you already be inside ring 0, the transition to ring 0 again? When can it be? Well,
Like if there's an issue during boot.
it's true that it's hard to, the most intuitive example is when we are at the very first instruction of this naked Asm function, right here, right? We didn't yet push anything on a stack. But one would argue that the hardware probably already pushed something for us. Like if we were transitioning from ring 3 to ring 0, the hardware would probably push those 5s, and they should exist. They might mean something else because immediately, like imagine you are like implementing either one interrupt and you didn't disable subsequent interrupts. You landed on this instruction, hardware pushed 5, and another interrupt shows up. And at this point, you say, look, like hardware pushes 5 again, or like now hardware pushes 3 and stuff like that, right? So these two other ones are dangling, and they don't mean what they're supposed to mean. They don't mean the stack pointer RST and stack segment, because they point to something else, right? So it's less of a problem. So it's not, at least it's not a stack fault, but just the meaning of these two fields is not very well defined. That's okay, right? So ugly case, but not. But at least I would strongly assume that these 5 are pushed atomically by the hardware, and they always will be there. So probably the only reason when it can happen is that when you mess with the stack, meaning that you say, look, I'm already in ring 0, and I was running on some kind of a stack, and I suddenly, like on entry to another function, like typically Rust allows you to either roll this stack, or alternatively can support disjoint stacks and essentially say, look, I detect the condition every time you enter a function that I actually need to extend my stack. Like roughly speaking, there is a prologue which will kind of link the stacks together, and just to like start using the next sequence on the stack. Just to, because in Rust, if you're running out of stack space, it's unsafe, right? It's below the language. So then, you know, your safety critics go to hell. So typically Rust runtime tries to essentially prevent you from running out of stack space. And essentially there are different modes how the language can work. This mode was definitely used in the past. I don't know if it's used right now, but the idea here, I mean, let me explain the modes. Do you understand the problem that in Rust, you may run out of stack? Actually, Rust uses stack heavily because, you know, you allocate on the stack a lot and then move on it, right? So what is how to prevent this unsafe condition when like, suddenly you run out of stack space and spill into some other space? Like, how would you do that at the level of the Rust language? Just to, at least to detect this condition and maybe like stack canary. So what are those?
You just put a special value on top of the stack. And then you check it every now and again. And if you overwritten it with some other value, then you know you blow up your stack.
Right, but what does it mean? What Daniel is suggesting is the following. He says, okay, the stack grows down, and put some magical value here, canary. And every time we enter a new function in Rust, the compiler will inject a tiny sequence, or maybe even before calling the function, depends how you want to build it. This sequence just measures the distance between the stack value RSP to the canary, and maybe it knows the statically compiler says, okay, I know so much stack, maybe there is no recursion, maybe there is no answer, but hopefully there is an answer. And at this point, this prolog says, okay, guys, oh, Jesus, like I'm running out of stack space, right? Because I know that it's too close. I will not be able to allocate the variable which sits here, some array here. And at this point, you can either panic or try to grow the stack, right? So my trick was my kind of linkage and essentially switch to a next section of a stack and start allocating this array on the next section. Make sense? I will fight a little bit back against this idea of using a canary because you don't really need a canary. If you, for example, make an assumption that the stack is, let's say, 64 kilobyte in size and 64 kilobyte a line, then you can take the value of RSP, mask it, and you already know the distance. So you don't really need the canary, right? So you can compute the size of the stack. But that's one way to go about it. The disadvantage of this approach is that it requires like a memory allocation. And it turned out in the past when people started running some regression tests against some Rust programs, they say, look, guys, if you oscillating around this point where like you're calling foo in some kind of a loop, you constantly like allocating this stack. When foo exits, you deallocating it, deallocating. It's just too much of a performance hit. We don't want to do it. And if I remember correctly, a couple of years ago, they switched to a different model where they say, look, we're not going to do it. We'll just simply panic in this case. And moreover, and again, you can always compute the distance and cleanly panic. But what I think x86 implementation, at least back then, a couple of years ago, is that they leave an unmapped region of space below the stack, which is called the guard page, right? Similar to how x86 was using the guard page, meaning that if you suddenly, then you don't need to write any code like this. You just blindly try to allocate. And if you, like, maybe you have to patch continuously your allocation, but essentially you hit the guard page at some point and then it poses an exception. And the operating system and the runtime is smart enough to tell you, okay, you ran out of space, so we're going to terminate the process, right? Guard page is the trick just because it's safe. It saves performance essentially, right? It's a little bit like it looks kind of ugly and patchy, right? So it's feels unsafe. You say, look, you can run out of stack space at any point, and then your computation is terminated, right? So you have to deal with like in your own way. For example, you can say we're going to run a static analysis and compute the max stack size and ask the operating system to allocate this stack size upfront, and we will hopefully never run out of space, right? Stack space. So if you don't have recursion, then it's doable. Make sense? Two things. What I was getting to is that in this esoteric setup in which you configure your operating system kernel to maintain this linkage of disjoint stacks, you may end up with a page which essentially is empty, and you will be interrupted right when you kind of switching to the new stack. So essentially, if it's a new page is here, you set the stack, the RSP point to the beginning of the page. At this point, interrupt hits, and your data structure spills past the stack, right? Theoretically possible. I mean, in practice, if you build a kernel like this without a protection, you'll get exploited. Someone will look at your code and say, look, guys, wow, I see an opportunity for an exploit. So we'll trigger this situation. So you cannot just like hand wave and say, look, like just leave it. It never happens, right? So what's the possible solution? How can we, second thing which I wanted to discuss is that we kind of dived into the problem of those stacks, right? We're not yet fully there, but at some point we're running Rust. Right now, we just, when we, in your homework, you put it into Rust, you just say, okay, here's some stack space, which I forgot exactly, 64 kilobytes or something we allocated, right? And we just blindly started running on these stacks. But this problem of running out of space is upon you. You didn't hit it, hopefully, yet. When I was building my own very first Rust kernel, I was saying, okay, like two megabytes for sure is enough. And then as we start developing, we will have some weird cases where essentially we spill out of stack and then it just crashes in some mysterious way. So essentially, it will hit you as a kernel developer. So we have two things to solve: normalize the entry, interrupt entry, and think of how we want to handle stacks in a kernel. Like, again, do we want to do a guard page? For sure, we can, but then don't forget to make sure that you have to touch everything between the current stack and the guard page, because what if you're allocating something so big that this big spills past the guard page, and you start initially like touching something here, go forward, and then maybe later in your code you touch the guard page here, crashing there. So like it's all a little awkward, right? And maybe this is so big that it actually, like, if you spill past the guard page and you're touching this code, obviously it's an exploit because you're touching either heap or something else, right? So meaning the high level conclusion here is that the guard page is only as good as it is, right? So you really still need compiler support to somehow make sure that you touch everything and making sure that you always hit the guard page sooner than letting attacker to hit it in your code. So two things: stack and normalization. Okay, so first of all, like, did you get the point? So it can happen that those two things either not well defined because they are sitting on top of a previous interrupt, or some esoteric case can even point to an unmapped memory and will crush your code, right? Okay, we got this. How will we normalize? What's the approach, you think?
What about if not null?
Like what?
Like if RSP and stacks have been very equal to 0, then it's more than we push them every time.
Okay. I kind of agree with let's just start over. We've already know what we want, right? We want this save data structure on the stack. Imagine this is our kernel stack pointed by the TSS. What do you do? What's your approach?
So it's one structure that we're pushing. If RSP and stack segment are not required, then we just push zeros for them.
Mm-hmm.
And then push everything else.
But what if they already pushed by the hard?
So, but we assume that they'll all get pushed to common key.
Correct.
So
We know that something is pushed. We don't know the length of this.
Do we know which ring we started in?
You can check. Yeah, you
Can
can
we check if it was 3 or 0? And then we read that they're 3 or 5, re-pushing them and added to 5 size struct.
Yeah. There is addition, like, I agree with this approach. This is what Linux is doing, right? And this is what I push for you to do in the homework. Just even if it's not fully correct, it's just a good thing that you think about it. The problem is that these two mysterious fields, stack and stack segment, they are pushed first, right? So kind of, you cannot like be somewhere inside the interrupt and say, I will push them later, right? Because that flips the order, right? So how can we deal with this?
This branch, if we came from ring 0, push 0, else push copy.
Correct. So agree with this. And I agree with this. So what you're saying is the following. You're saying we, irrespectively of what the hardware pushed, we will forget about it and start clean with our own data structure. And there are two options. If we came from ring 3, then we'll just copy these values here, right? And this will be the beginning of our well-formed stack rate, right? We say, look, if we came from ring 3, then we copy those 2 values here. If not, if we came from ring 0, then just push zeros, for example, or push real values of the register P and SS by note, right? You just have them. And then, you say, look, we know for sure that the hardware pushed these 3, right? So, well, sure, we'll copy them as well here, always copy. And we'll have our versions of, what is that? Our flags, I forgot exactly the order of flags. Our ID and full segment. And then we can solve it at the level of a type, because whether the exception pushes the error code or not is defined by the type of the interrupt, so exception, basically by the number. And essentially, again, we need an if, right? So we say, look, if this one pushes it, then we will copy it from here to here. If not, we'll push the 0 as an error code, right? And after that, we push all of our general registers, RAX and whatnot, the R15, and pass the pointer to this data structure to our handler right here, right? So which means that if these 2 were not pushed, at least they are not dangling, because our data structure ends here, right? And it's all safe and well formed, right? Make sense? And this is what Linux is doing. What happens if we are interrupted concurrently, right? We were inside this code trying to push everything, and we pushed half of it or copy half of it, and then a new interrupt came and such. It seems to be fine, because you will start over. You might end up you will know that you are inside ring 0 already, so you will initialize those values, but again somewhere here correctly, right? And when you IRAT from the interrupt, you will end up back on this instruction, continue forming this stack. So we can support nested interrupts, right? Agree? So that seems fine. The solution seems fine to me.
What's the mechanism for detecting which ring you
You
I know we've been ignoring rings 1 and 2, but are those also, do they fall under the 5 or the 3?
I don't know. I never used them. I think they fall under transitioning from ring. Any change of privilege probably will push 5. My guess, but I never used ring 1 or ring 2, so I don't know the answer. How to detect? I forgot exactly. I mean, I can quickly look. I mean, like specifically, this is exactly what I was doing when we were working on Redleaf. I first looked at the interrupt convention, and then I said, okay, no, it's not gonna fly. So what I did here, this source code comes from Linux, meaning that I took this entry _64s from Linux kernel and put it in this Rust kernel, which we were working on, and I was responsible back then for building the interrupts. And Linux does this, I think, right? So what they do here, they first allocate space for this 5 on the stack, maybe for all 6, right? With this macro. Then they use a macro to save like general registers. I forgot exactly what is CRAX and what is extra rax. And then they do test this code segment. And what's the test here? They check whether this, and because, what is that? Code segment. They checked for the field of this CS, which got saved on the stack, and they checked whether it was ring 3 or ring 0. That's the test, right? Because this is always pushed. And you can always check it and think, okay, is it 0? Then you came from 0, and then you do like all this, whatever, padding. Or is it 3? Then you came from 3, right? And that's essentially what I argue you should do as well in your code. I wouldn't say like copy from Linux is too, like, we will do something simpler, and we'll get to this swap fast thing later, but at least for now, we kind of get the solution how to do it. If it will not work always, that's okay, but hopefully it will work at least most of the times in our case. But probably it's not hard to debug and everything will be running fine. Any questions about this? Make sense? Like Linux, like I was saying, there is a guy who wrote a book about every line of this macro, and I had to read it because I wasn't able to understand. Now I don't even remember what Linux is doing. So there is like a ton of corner cases which they want to we'll handle probably a subset of those. Okay, so stack normalization is there, right? All clean, right? I just wanted to cover one extra thing before we start on the interrupt controllers. So, okay, but just again, just wanted to 100% make sure this idea is clean, right? Clear to everyone. It's just because, you know, like if you just read the Phillips blog, you might get confused about what's involved, how it works. Okay, one other small things, right? So, one other small thing. So I keep saying that we're gonna save general registers, RIX, RBX, R15, right? All of this. Why don't we save anything like AVX registers, like vector or NMX, like essentially floating point and vectorized registers, because they do exist, right? I mean, in fact, if you disassemble both LLVM and GCC generated code from nearly any language, but let's say C, C++, Rust, you will see wild, they will be used quite a bit, right? At user level. So can someone tell me what happens? Like if I have some AVX instruction here, AVX is like 512 bits long. I mean, there are different lengths of AVX, but you do something like you build a hash table and suddenly an interrupt came, timer interrupt came, IRQ 32, and you're transitioning into this make assembly handler. And you did this stack normalization, like we just talked about, and you push general registers here. What happens with AVX? Why we never talked about them. I just wanted to make sure that everyone's clear again on this one.
Since they're, I'm assuming strictly user level like instructions or registers, they'll either be saved on the user stack or used process and only used there.
I'll take this answer, but maybe there will be some other ideas.
Mine was similar as well. Maybe they know for a fact that the kernel will use these AVX registers. So the kernel will use.
Correct. And if it's truly so, you say, look, and to know for a fact, you really have to disable the use of AVX registers in the kernel. If you read through Philip's blog, we did it. Like in our build system, we actually did. We say, look, let's compile kernel without the AVX registers, right? Which still doesn't fully solve the problem, because you say, look, that's fine. If we just simply handling an interrupt and returning it to the user, and the kernel didn't type those registers at all, then everything is intact, everything is fine. If we do a context switch to another process, like in x86, for example, then at this point, we still have to save those registers, right? Because other process might be using them.
Yeah.
And so you will have to, when we switch from one process to another, we will save extended registers. Those are called extended registers, as opposed to general, right? Save extended registers, right? Makes sense? Okay, that's one way to go, and hopefully, and arguably, or whatever, realistically, I guess that's what we're going to build in our kernel, and that's what we typically build in my lab as well. What's the trade-off here? Like, is it an ideal choice or not? Like we gave up the use of AVX registers in the kernel. Is it idea or not? Why not? Performance, right? So what would be your guess? How will it affect performance? Probably, yeah. Or what kind of like kernel? I mean, I agree with you, and this is what I wanted to hear. So, meaning that you have design choice. Either disable the use of AVX registers in the kernel and accept the performance penalty. It's not just a penalty, because at least on entry into the interrupt, you didn't save the extended register, so there is a slight performance gain here. And then through the kernel, you're losing performance probably. But you know, you're not saving them here on the context switch. And the question is like, is this losing AVX registers outweighs the loss, like outweighs the cost of like of not saving them here on entry? And there is no like easy answer. It feels I was building kernels without AVX, but it depends on what's in the kernel. So if it's really a very small microkernel, which just like picks the next process to run and switches to it and then whatnot, and nothing like, you don't probably lose a lot of performance due to the loss of AVX registers, right? There might be some, but it's hard to quantify. I don't know the answer, so like it has to be a study, right?
Yeah, like I wanted to ask if there were any benchmarks on like your file system hash tables using.
Correct. So no, and this is where we like. But if your kernel is like a full-featured kernel like Linux, monolithic, runs a file system here or a network stack, does something like RAID, right? So just like some kind of erasure coding or something, anything what requires any kind of computation, which is probably quite often today, like even this crypto or whatnot, like you're encrypting the SSH connection. Then you kind of screwed, right? So you say, look, I'm probably losing too much. You can play tricks like Linux does. So most of the kernel doesn't use floating point registers, and then suddenly you enter a function, and that function saves the registers, starts using them, and then restores them. That's another design choice. But clearly, if you're doing some kind of crypto compute thing, then you need the registers back. And I just wanted to make sure that you're clear on what the design choice is, right? So for our case, I would say, forget about it. We're not going to run file systems, network stacks inside the kernel. So we'll be fine without AVX. Let's not save them. Save them, we just will save them here, and we will be switching from one process to another. Linux does something similar. So the Linux still doesn't use the AVX registers in the most majority of the kernel, with some exceptions, like really there are crypto functions, then you explicitly save and restore the AVX registers. Make sense? Okay, that's what I wanted to talk about. One more thing. Okay, we got this. We understand what's going on with AVX registers, right? Any questions? And finally, Jesus, I mean, like, I will never get to this, to the interruption. We're almost there. Finally, there's this mechanism which is worth discussing. Like, imagine you're running in a kernel. Imagine your TSS points to the kernel stack. Imagine, remember our discussion about guard page. Imagine we're so clever, we put a guard page here. And I will show you how to run static analysis. Imagine on the kernel, LLVM return us at okay, we should be good with 1 megabyte of stack. We allocate 1 megabyte for the kernel. But this computation isn't precise, because if we enable nested interrupts, right, we can actually, like LLVM says, okay, a timer interrupt will never take more than 1 megabyte. But what if I get another interrupt while running a timer interrupt, right? Then you kind of like very realistically may run out of stack space. And imagine we are so clever that our guard page is just very, very long, doesn't fit on the board even, right? And so instead of like just blindly spilling over, we actually hit the guard page. Just like second interrupt, or like you were running something, and maybe we're hitting the guard page at the very top. At this point, what happens? Guard page is a page which is not mapped by the page table, or is mapped with a permission which says, okay, when you read or write or execute, no, execute, you don't execute on a stack. So it's executable but not readable, writable. So the moment you read or write it, you immediately get a page fault.
Does that trigger a double exception? And then
Correct.
Because it tries to then post and it can't again, a triple, and then it crashes?
Correct. So Talia read the something, that's good. But no, this is what I wanted to make sure that we all understand, right? It happens in practice, and that's why it exists. So really, this is a page fault. So it's not a double fault yet, but like it's not a double fault as a separate double. First, it's a page fault. The hardware tries to push this whatever 3 things on a stack, right, to like let you to process the page fault. But this is the guard page. The stack is pointing into the guard page. And at this point, the hardware cannot push. The hardware itself catches a fault. And at this point, it's a double fault. This double fault is really like an entry in the interrupt descriptor table, which I forget exactly the number, but which one is that? Like number 8, right? So there's a specific entry reserved by interrupt descriptor, and there's a double fault. We'll try to deliver this exception, right? But obviously, like it tries to push something for the double fault, right? But it cannot, because this is pointing into the guard page. At this point, it's a triple fault, right? There is no entry for triple fault because the hardware says, okay, we're not going to let you handle triple fault. At this point, things are so bad, typically it's a reboot, it's a reset of the machine, right? So how can we deal with this ugly case of a double fault? Tell us. Whoever read the blog post. Anyone read? People read but do not want to tell everyone.
I don't remember.
You don't remember?
But I did read it.
Yeah.
It seems tricky because if it couldn't write to the stack, then you don't have what's needed to return to the caller for the initial faulted interrupt.
Yeah. And well, there is no magic solution, but Intel helps us. And they say, look, guys, you actually can allocate a couple of other steps. And TSS not just will have a pointer to this kernel stack, but we'll have 7 more pointers. Why 7? Because they said that we have space in the interrupt handler. We have 2 bits, so you can specify 8 different numbers. But 0 means that you go the normal path and choose this stack. And if this one is not 0, but let's say 1, then the hardware will choose one of those 7 stacks. Those are called interrupt stack table. I forget exactly how the stacks are called, but essentially the idea that TSS itself will contain also 7 other pointers, potentially, if you want them. If you don't want them, you don't have to. But at least probably for this double fold, it makes sense to at least say, like this thing, it will be pointing to the, this is the line underneath, will be pointing to this extra emergency stack, right? And which means that the first time you hit the guard page, the page fault, it's up to you. You might service it on a separate page fault stack if you like, which maybe makes sense, but maybe you're sort of, you say, look, I don't want to deal with all these stacks, and only the double fault will switch here, and the handler will start executing on this IST stack, interrupt stack, table stack. And the same kind of makes sense to do for this funky non-maskable interrupt, because non-maskable interrupt shows up even with other interrupts disabled, and it's just too hard to reason that your stack is well formed. And so probably non-maskable interrupt. So at least double fold and non-maskable interrupt probably makes sense to have them on a clean stack, which is available to you. And the second NMI will not be delivered. Double fold, you probably will configure it that disable subsequent interrupts, but NMIs can still be delivered, but at least it kind of like separates all the stacks and like life is a little better, right?
I just need to make sure I understand how popping these stacks. So when you do, is it called IRET? When you IRET,
Mhm.
does it just pop off the current stack that like where ESP is pointing to?
IRAD assumes that depending on whether you IRADing into ring 3 or into ring 0, again, the same kind of asymmetry thing, 5 and 3.
Yeah.
Let's imagine we're going to ring 3, for example, or let's go ring 0. Then IRAD assumes that you are at the very top of the stack are those 3 things which you want to restore: R flags and code, RAP, and code segment, right? And it will just blindly restore those and we'll jump to this. It doesn't have to be like, of course, if you're transitioning into ring 0, then it will restore the stack, RSP, and stacks segment as well, right? And those will be your new values of those registers. And if you're returning to, depending on what value was saved here in the code segment, then it will just restore this thing, right?
Okay, so
And technically speaking, if you're doing this, the stack may not be contiguous, right? So if you say, okay, there is still something sitting on a stack, but I'm returning to user level. So at this point, just whatever. Next time we start with the next interrupt, the TSS will point to the beginning of this.
so when you're done handling a double fault, the IRET will just handle it properly. Because it'll be pointing to that second stack.
Good
so
question.
it'll-
Very good question. Yeah. So because like ideally you assume that the hardware pushed whatever 3 things here, RSP is one of them. And when you do IRAT, and this was your current value of RSP, then this one was pointing to somewhere. Hopefully you will fix it because you're on a guard page and maybe you will terminate something. Maybe there is no fix, but no logical meaningful fix, right? But it will follow the protocol and you can control what happens, right? It's kind of like, if you're a language person, it's your like continuation passing style. So you say, like, continue there. I don't really know the past, but it will make sense in the future anyway. It makes sense. But this is a good question. I kind of,
Actually, yeah, if it pops off to the guard page, will it be painful again?
yeah. So you shouldn't probably. You should like either say, look, guys, this thread will never run, and you will pop to something, and this one gets terminated. Not a good idea because cleanup of resources.
And then be able to handle.
Correct, right? So at this point, you're already half broken. Like maybe there is a way, and you very carefully, your kernel is, and everything is designed in such a manner that it can handle stack overflow. I mean, it looks to me that the only possible way to solve this problem is to grow the stack.
Yeah.
And just let it run and hope. And maybe there is a procedure for how to grow, like do this kind of linking of different disjoint stacks. Maybe there is a way to even migrate the stuff from this, which was allocated here, to some other stack and continue.
So one of the others have.
Yeah.
Yeah.
But you have to do something. It's good that you're thinking about it. Yes, meaningful is totally non-trivial, but it can be done, hopefully.
You know, that's what I was gonna ask, like, we can detect that we're getting close to the end stack. We have extra stacks, so why even deal with the card page when we can chop it?
It depends on how you construct
Yeah,
it.
right.
No, hold on, I'll take it in a second. I don't think the default compilation, when I looked a couple of years ago, the default mode in Rust is not to check for, are we close to the stack? the default mode was that the runtime is assumed to have a guard page, and then you hit it, and then after that recovery starts. And recovery is not specified. There is no way, as you're right, I agree. I don't see a meaningful way to recover, but that was the default mode. And there was some legacy mode in Rust which supported this checking for the stack space. And actually, I think for the purposes of safety, we actually enabled it in this the kernel which I'm using as an example here, this Redleaf. I forgot exactly what decision we made, but because this was unsafe and we wanted everything to be safe. And I think we enabled this mode with a slightly slower mode where you check for the space and go forward. But still there is this probably awkward window where you're checking for the space, but maybe some other interrupt comes. And you can't even reason what if there's no space at all and this next interrupt is completely screwed. And I think the answer was, and I'm not sure exactly how we did it, but the answer was that all interrupts are actually on an IST stack. At least we have a guarantee that we can possibly, but along those lines. But I get it. It gets very complicated. I could have just teach you a short story and then like it was in x86, right? x86 doesn't do anything with this IST stacks. It doesn't do anything with double fault. If you run out of stack space in the x86 kernel, you just panic and that's it, you reboot, right? But since we're in this class, this is the reality of life, and I'm not exactly sure that I can teach you a very good solution, because it depends on what is it you want to happen. But at least you will understand that, first of all, when you see this in Linux, you say, okay, I got it, I've heard of it. Linux is in trouble, but they try to solve it. May probably solve it in 99.9% of cases, but there's probably some corner case when they crash. I don't know if they know it. It's stability of security attack. And I also wanted you to kind of at least think about it, right? And Philip does actually mention IST and everything. And that code, which this from Atmosphere, which was setting up the global descriptor table, was also setting up, this one, was also setting up IST and the TSS. Where is it? But I forgot how it was used, but at least those are these, so it's from 0 to 7 IST stacks in red, or in this atmosphere. Okay.
Does it ever make sense to grow the kernel stack and replace the guard page with more stack space and move the guard page down?
Well, as I say, I'm not exactly sure I can teach you a solution. Probably. I would say if you're clever enough, you have a giant guard region, then you can probably try growing to at least handle this emergency case. And then at least say, look, guys, in most cases, I'm okay. But if you want to build a formal argument, whether you ever can run out of guard pace, it's hard, right? So I don't know. If you just hand wavy, then fine, it's okay. If you want to build like a mission critical device, like some medical, insulin pump or something, and guarantee that this cannot be exploited, the pump will never fail, then this argument becomes hard. I would probably go the way, some kind of like static analysis, saying that like on all these flows of execution, we made an analysis and argument that the stack we never run out of stack space to begin with. Then you probably don't even need the guard page if you have a formal proof that. But it's hard because then you have to, it's probably beyond static analysis. It's more like formal verification to make this argument that static analysis is only as good as like, heuristic, right? You have to trust it. I mean, most people do. It's better than just human argument, right? But a very formal argument requires complete functional correctness of the code, saying that no matter what happens, we always can reason about the size of the stack. There will be no pointer dereferences in some kind of a cycle. Make sense? Wake up. Okay, good. So we understood IST. The name for this is IST, interrupt stack table. We might come back to these stacks in the homework, we'll see. Okay, good, but I'm now finally done. So like with this, we are ready to enable interrupts and get going. Essentially, I explain all the stacks, all the interrupt descriptor tables, all the global descriptor tables. We can start coding. Every line of code now makes sense. Finally, let's try to enable external interrupts, right? And what it means is that, of course, the interrupts like page fault and everything, they are always on. Even if they needed to be enabled, Intel does it for us early on in the boot cycle, like not the boot, like when they initialize the CPU, whatever they do, probably they're just always on. If you want to get an interrupt from a keyboard or a timer, you really have to talk to a piece of hardware which says, okay, I'm ready to deliver the interrupts, right? And in the past, Intel was using this mechanism called programmable interrupt controller. And now they kind of abandoned it and they switched to a couple of local advanced programmable interrupt controller and the IO APIC. So let me quickly go through the legacy pick. To go from like the reason I'm doing it because Philip wrote a lot of good text about it, right? So and it makes sense to kind of like at least read through to understand how it may work. But I argue that in our kernel we switched to a regular LAPIC plus IO APIC bundle. The thing is that where is it? Let me just figure out his blog post. Apologize, just a sec for testing. CPU exceptions. Just quickly. Yeah, this like what he says is that look, in the past, the CPU itself was one piece of hardware. There was a different interrupt controller which was sitting on another, and essentially it had some programmability. But essentially, the idea that two different buses on the CPU, it could receive like events from timer, keyboard, other hardware, and so on. And then there was a specific protocol it was following to, and you could program it a little bit to essentially trigger an entry like a timer interrupt. Remember the interrupt descriptor table itself, the first 32 entries are reserved by Intel, but after that you can technically pick any entries, and essentially those machinery was allowing you to map. In fact, I mean, you could have mapped interrupt to come in as a whatever, as a page fault, but that's not ideal because then you have to distinguish whether it's a page fault or a timer interrupt in your kernel. So that's not fun. And this programmable interrupt controller was allowing you to like remapping those inputs from a timer, typically just for historical reasons, but there is nothing really fixed about it. Timer interrupt is mapped to, if this one starts from 0, this is 31. Timer interrupt is mapped to entry 32. It's the first available entry, right? And again, in the past, like really, it was a combination of two controllers which were connected in this hierarchical manner. So there was a primary controller here, which was handling like timer, keyboard, and there was an input from a secondary controller, which was handling some other, external events. And some of those were available, and you could buy like a new piece of hardware, put it on the motherboard, and then you could configure those jumpers like this input to the interrupt controller. And then essentially, it was reaching the CPU. So what Philip is doing here, he says, okay, look, guys, I have a crate. I think he wrote it. And essentially, this abstraction of these chained controllers is like essentially implemented in Rust. He provides two offset to essentially map the entry of the of this first input timer to entry number 32, and then whatever the entry of the second controller is, since this one has 8, so it's +8, so he passes it here, essentially, what's important here is that when you boot, the hardware will not send you any interrupts. So you have to explicitly enable them. Of course, it's not this STI flag. It's just program the controller that at some point you're ready to receive a timer interrupt. And you can, I think, keep some of those interrupts disabled and some, and they use word mask for disabled. And some of them can be enabled, right? And then you just go essentially at some point, you say, look, somewhere during your boot routine in your kernel, you say, look, at this point, I'm ready to enable the interrupts. You say, look, I enable the controller, and then you enable the STI set interrupt flag instruction, making sure that both the hardware and the software can deliver those interrupts. One additional interesting detail is that it turns out that you have to explicitly acknowledge the receiver of an interrupt. And otherwise, like in his example, he configures the timer interrupt and he puts the handler in the interrupt descriptor table, like just an entry timer, puts this interrupt handler code here. And what the code is doing is just puts a dot on the screen saying every time you receive an interrupt, I will just print a dot on the screen or serial line. And he talks about how like he uses this, he likes this lazy static, like that's his deal. You can write code without it. If you will, Jafang writes without lazy static. But the idea is that you only receive one dot because essentially the hardware says, okay, I send you an interrupt, but you never said, yes, you're done and ready to receive another one. And so you have to explicitly acknowledge the end of interrupt. And so essentially there is some magical code which says, okay, it communicates with this programmable interrupt controller. We can go into like in a specific assembly sequence which does it, but just writes it some IO port specific numbers. And at this point, it says, okay, look, guys, we actually acknowledge that interrupt was received, and the hardware will send you the next one, right? So it's not just like STI and clear and set the interrupt flag. Also, you have to talk to the controller and essentially enable, like acknowledge the interrupts. And then you receive like all these dots, right? Like here in his movie. Make sense? And the same applies to this local programmable interrupt controller and X-Epic, which I will discuss in a second. Of course, like let's do the controllers first, but like I will cite this post in my lectures and in the homework. So I recommend you to read it just to essentially walk one more time again, like around through the problem of deadlocks. So what is the deadlock here? Do you guys remember from x86? What's the problem with interrupts and that? What kind of deadlocks are possible? Wait, remember guys, Rust is a good language. Single ownership. Races are supposedly impossible, right? Because only one person can write one context, one scope of execution. And moreover, when you can write, you cannot read, right? So no races. So if you like wrap everything in a mutex and stuff like that, so supposedly everything should be fine.
I'm guessing in x86, if you lock to notify the controller that we're good, and you get interrupted in that, the lock wasn't free. So now you try and lock again to notify that you're good, and the second interrupt, you get stopped.
They agree. Not entirely sure what you said, but let me explain the simple case. Imagine you go like through a syscall, like you enter the kernel. At some point, you acquire a lock, like a mutex on some object. And you have a whatever mutable reference to this object under the mutex, right? If at this point hardware interrupt is triggered, you go through the interrupt descriptor table, you start executing your handler, and imagine it so happens that you try to acquire the mutex for the same object, right? Here, that's a deadlock, right? Because clearly you just will be waiting on this mutex forever because you preempted execution of this thread. And maybe, as you said, maybe it was a syscall. but maybe it was another interrupt. It doesn't matter. So maybe you were handling some other interrupt, and this thread of execution is just like previous interrupt, and it acquired a mutex, right? Agree on the deadlock problem. So how do we fix it?
I was reading about how Linux does print K, and if they're not able to acquire the mutex, but they use a semaphore, then instead they write the contents to a buffer, and then the next time that the mutex is acquired, that one prints what's in the buffer, and then what it wants to.
Okay, that's a clever solution. I actually didn't know that they do that, but what you're saying is that you know that such case that imagine this is a buffer. And when you're designing your code, you have a line of reasoning saying that, look, I know that if I acquire the mutex, the deadlock is possible. And what you're trying to do, like you write your code in such a manner that you kind of say, I will try to acquire a mutex. If I fail, I will maybe save this data in some local buffer, and it will be maybe like spinning, or in this case, we have to return, and then this has to be picked up by some other code of execution, thread of execution, and then maybe acquire a mutex and merge into this object, right? That's a complicated synchronization scheme. I see how it can work with serial line, because even if you miss, like reorder some outputs or something, it's not a big deal. You can imagine that like something more semantically complex will, while theoretically the synchronization scheme is possible, it's hard. And I'm not saying that, okay, guys, never do it. Maybe it's a sound way to do it, but nevertheless, let's come up with something simpler, which we can more easily write code without thinking too hard or building mathematical proofs that, you know, the synchronization scheme actually is correct. So how we're gonna go about it? How does x86 solve this problem?
Is it mass neural superview requirement?
Correct. So the solution in this x86 is never acquire mutex with interrupts enabled. I mean, it slows you down every time you acquire mutex. Before doing this, you say CLI, clear the interrupts, and after that you do it STI, and you also do that in some kind of a nested, you know, if you have multiple CLIs or something, you have to count how many you did, and did STI only once when the last one is released. But at least you know that interrupts are temporarily disabled, and so you avoid this deadlock, right? Everything is fine. What about non-maskable interrupt? It's always on. Just wanted to again make sure that in this class you guys are, you know, the state of the art, the pain which we go through every day. No non-maskable interrupts. They don't obey STI flag. They will be delivered. So what will happen if you do it? And mutex there. Deadlock again, right? So like maybe at this point we're back to what like, oh, I mean, do whatever you want. Maybe no mutexes, no synchronization, but yes, it's a danger zone. So that's why non-maskable interrupts in general is a not very good idea. So do something very clever. Maybe you have to go and reason about the states of objects which you acquire, and you can have a logical argument that this non-maskable interrupts only acquire mutexes, which are only used from other non-maskable interrupts, which solves you synchronization across the cores, because each core will be processing its own non-maskable interrupt. But at least you avoid the deadlock. But it's essentially, I don't think there is like a simple, elegant solution. So it's up to you. And it's not even like domain of operating system. It's probably just general, whatever, parallel programming, concurrency. It's just that typically no one wants to talk about non-maskable interrupts. Probably the solution is to, a pragmatic solution, try to stick to lock-free code. Like if you need to synchronize, for example, if you have to add an element to a linked list, make a lock-free linked list, you know, compare and swap those instructions, which essentially, like, because if you fail to insert once because someone was inserting concurrently, you do a next iteration of a loop, and then you insert a next element of the list, right? So log-free data structures is a good answer. If you want to maintain some stats, just do like again, atomic increment and decrement instructions. So there's a like subset of log-free data structures. You can, after that, it's like your kind of open research argument, how you want to structure it, but essentially be very, very careful in your non-maskable interrupts. Otherwise you will have deadlock. Okay, let me like stop here and I will come back to the controllers. The thing is that I'm traveling on Wednesday. So I want you to start on the homework. So which while I keep promising that I push it, but I'll literally push it today or tomorrow, realistically tomorrow. I want you to start working on it. Support for interrupts. Programming interrupt controllers, I will just give you a blow and you will just invoke it. And I can explain it next Monday when I'm back. We will talk through it. It's worth knowing, but it's not like an urgent knowledge which you have to like, you need to know to start working on a homework. So everything else you know, you have like interrupt distributor table, you even have interrupt stack table, IST, so non-maskable interrupts, you understand them, so everything will fly from here. Stack normalization is there, and we talked about how we want to do it. So I think you're ready to go. And I will just come back and explain the how to configure the programmable interrupt controllers. Even with this code probability, get going fly, but it's so archaic that even he wants to give it to drop this and like write about real. He mentions that he will soon switch to a recent controller, but he never does it, I think. As of now, at least I haven't seen the text from him. Okay, good. So Wednesday, no lecture because I'm out of town. So work on the. I'm physically on a plane, so I cannot teach remotely. So that's it. I guess. Thank you, guys.